Hey everyone, welcome to another biochemistry optical core tutorial video. Today we're going to be talking about imaging with the box widefield microscope. So you might be interested in doing widefield if you don't necessarily need the optical sectioning of something like a confocal. Ideally, you might just want to take a lot of images with a very thin sample and just be able to take those images quickly and with decent contrast. Let's go ahead and get started. I have booted up the instrument. There's a video for that as well. You can check that out. And all I've done is double-clicked on this NIS Elements icon, and I typed in my user profile. But this is the next window that pops up after you've typed in or selected your user profile. And you can see that there's actually a host of different options here. There's 2 Andor options and 2 Hamamatsu. Andor just refers to one of the cameras, same with Hamamatsu. This microscope actually comes with 2 cameras that you can use, which is in contrast to something like the confocal where we use photomultiplier tubes. So these cameras are highly sensitive, but the Andor is a little bit more sensitive, which means that it's going to be better equipped to detect low levels of light and give you better contrast between background and foreground. So your signal you want to see, the foreground, versus the stuff you don't want to see, the background. The Hamamatsu is a CMOS camera, which its capabilities basically mean that it has a slightly less sensitive detector. It's still really good, but not really as good as the Andor. However, it is a faster camera, so it can take a lot of images much more quickly. So if you're doing time-lapse experiments where you might need to see some dynamics, you might end up choosing the Hamamatsu. Whereas with the Andor, if you don't mind not necessarily having the super fast speed of the Hamamatsu, instead you're trying to detect maybe dimly fluorescent molecules or something to that end. But they're both solid choices. You really can't go wrong with either one for most fluorescence applications. Today, I'm going to use the Andor, and we're just going to hit OK. So after that startup sequence, we are brought to the startup menu, or the main window, I should say, for Elements. Now, if you're opening up this for the first time, it's not going to look like this. I mean, in fact, if I exit out of a few of these things and just show you where these guys come from, you might have it look more like this. You know, if you start, for the very first time, you're starting your user profile, it might look like this. So I like to do all of my images in this dark mode up here. You can see you can choose either one. That's just because I do all my imaging in the dark. You can also choose a smaller font size. This can be especially helpful if the window is getting very crowded. Up here we have just optical configurations. I'll get into that in a second. And we have shutters here. There's a ton of different shutters on this corresponding to the light source that you want to turn off and on. So the ones we'll be talking about today especially are the SOLA. So the SOLA is our LED light source, and that provides all of the fluorescence light that we're going to use for taking a look at images today. I'm not going to show it today, but the DIA is the same one if you're familiar with the confocal videos. It's diascopic amplification. And that's just our bright field lamp. So these are both the shutters for those. So in order to see either one of these light sources, these both have to be turned on. Let's open up some of these GUIs again, because we're going to need to see the TiePad, the filters, to get started here. So I'm going to right click, and you can go to Acquisition Controls. And you'll want to select the TiePad first. So that's this guy. This is very common in all Elements that we have. Up here at the top, we have our objective choices. You can see I'm currently looking at the 100x. The light path, this is all viewable on the microscope itself, but you can press any one of these buttons and do the same thing. So E100 stands for eyes, 100%. That's how you're going to see through the eyepieces on the microscope itself. And then for today, because we're using the Andor, we're going to use the L100. That means all the light goes to the left side. And if you were to use the Hamamatsu, then you would use the R100, because the Hamamatsu is on the right port, and correspondingly the Andor is on the left port. As I said, I'm not going to be really talking about the bright field, but this is the controls for the bright field. In order to activate the remote control, you have to actually press this. This switch will usually be off, but this lamp will actually open the shutter for it. And then there's another shutter in order to actually see the bright field, and you'll have to press that here. So all 3 of these will need to be open, along with this being on E100. It can be L100 actually, but these 3 will all need to be turned on in order for you to see the bright field. But as I said, I'm not using bright field today. I'm just going to turn all this off and move on to the next thing. So This right here is really mostly for turf, but the big thing you need to pay attention to is that this needs to be set to epi for epi fluorescence. So if you're going to be looking with wide field, this will need to be on epi setting, not turf. Otherwise you won't see anything. And these are our set of filter cubes that are in place here. So if you hover over any one of these, they'll give you a little description of what this filter cube is. A filter cube just contains the excitation filter, the emission filter, and the beam splitter for generally a specific area of light that we want to isolate and look at. So they're usually very specific to fluorophores. This one's very specific to DS red, Tritzy, Psi3. This one is, of course, very specific to GFP, DAPI, and this is quad. We're going to talk about this in a second, but this is generally used for turf, and it's because it has multiple band passes, which just means it can allow in multiple wavelengths of light, not just some specific area on the visible spectrum. Similarly, this is for looking at CFP, YFP, and M-Cherry. But the big things we're going to look at today are going to be these three filter cubes. These are really standard, and the quad. So the next thing I'm going to talk about is our filters and all of our setup there. So to do that, we want to look at this right here. So this is our filters, shutters, and switchers menu. These are all of our shutters. As I said, they're also all up here. If you press one, it shows up in both places, so it doesn't matter what you choose. Finally, there's these filter wheels. So in order to use these different filters, we have to use a filter cube that will still separate the excitation and emission light and also allow a lot of these colors to also pass. So for that, anytime you use the excitation filter wheel or the emission filter wheel, you'll need to use this quad. So this right here is our excitation filter wheel. We have one that just blocks all light. We have one that lets in all the light. So this is ideal if you're going to use one of these three colors. You'll want this to be empty. And then all of these are specific excitation filters. And if you hover over them, they'll tell you both the center wavelength and the bandwidth of light that that filter will let in. So this one has a center wavelength of 350 nanometers, and it'll let in a total of 50 nanometers of light. So that means that from 325 to 375, it will let light in on the excitation side of things. Same rule applies here. We have a 525 nanometer center wavelength with a 50 nanometer bandwidth. So that means that from 500 to 550, this will let emission light in. So these are two pieces of the light path puzzle. And this controls the light that you filter after fluorescence has occurred in your sample. That usually means that these are all going to be a little higher wavelength, center wavelengths, than the excitation. The sample we're going to be looking at today actually does just use these three colors, but I will show you how to duplicate these colors with our filter wheels. So that'll just give you an idea of how you might structure your optical configuration or your settings to best match your label for yourself. To explain that, let's talk about GFP. If you wanted to, you could just click this button, and these both need to be empty, so no other filters need to be in place. So you could do this for just GFP by itself. That is totally fine. But if I wanted to better approximate GFP potentially, or I wanted to use these filters instead, what I could do is hit this quad button. And then I want to select the filter that is closest to the peak excitation wavelength of GFP. That just happens to be around 490, so I'm just going to select that. The peak emission wavelength of GFP, I just happen to know off the top of my head, I think is like 502 or 510. So we would want a center wavelength around 510. There's a 525 here, which that's pretty good. And so if I use this filter setup, I should see pretty much the same thing as if I just selected the GFP filter cube on its own. One last thing that I want to open up is this. There's actually a couple. So there's the light source has its own menu that you can select and choose the intensity of light. So this is currently set to 100%. I'm going to lower that to something much more reasonable, like 15, because we have a very bright sample. So this is, of course, the other ingredient, right? You've got your filters in place, but you also need to turn on the light source in order to see something. Let's see if anything shows up now. So that, you can kind of see it. It looks terrible. And that is likely because we haven't adjusted any of the camera settings. So that is the last step here. So to open up the camera settings, you just want to right click again, and you want to just click the settings button. These are the controls for your camera. There's an exposure time. As you can see right now, it's really low. That is actually probably the reason why we don't see anything, is because 1 millisecond is very fast exposure time, and we have a really low gain. So I'm just going to increase these a little bit. So the exposure time is how long the camera is open to receive light. So the longer this value is, the more light that's allowed in, and the brighter your image looks. Alternatively, you can increase the brightness of your camera by using the electron multiplier gain multiplier. This is where the and/or strength comes from. You can use this additional multiplier to add gain to your sample and really increase the brightness of your sample. But this will increase noise in your image as well. So keep that in mind. The higher this value is, the brighter your sample will appear, but you'll also be introducing noise to your image that you'll also see. So if I hit play, we should theoretically have a better looking image. And we do. Again, the primary ingredients for just showing an image here was I needed to have the shutter open on my light source, my excitation light source. I needed to have the filter turret set to a cube that will allow light in from a lot of different colors. And I needed to have an excitation and emission filter set that are specific to GFP. Now, if I select this filter cube that's specific to GFP and change these to empty, because I have a filter cube that has all these excitation emission filters already in place, I should see roughly the same thing. So let's take a look. And I do. It looks exactly the same. Because all I did before was I approximated the filters that are in this filter cube with the filter wheels that we have. So I talked about the cameras. Now all of these settings right here fall under the settings you would want to use for something like an optical configuration. Now optical configurations, I have a whole video devoted to this for the confocal, but it turns out the same principles all apply here as well, because we're still using elements. So if you look at that video, it goes into in-depth about how to make an optical configuration. So let's say then that you've determined, you've made a couple presets, you figured out the image you want. Now the last step is to put it all together and actually create an image. So to create an image, you're going to want to use a specific window called ND acquisition. So to use ND acquisition, you just want to right-click, Acquisition Controls, ND Acquisition. Almost always you're going to be running this wavelength one, because this will contain all of your optical configurations. So I just want to check this to begin with. I'm going to take a look at my path that the files get saved to and the file name. So I've made a folder on the desktop for this image. Now I want to populate this with my actual wavelengths or optical configurations. So to do that, I'm just going to check this, and I'm going to load in my first optical configuration. So that's going to be DAPI. It says DS Red. I'm actually going to keep DS Red, and I'll just reorder it. And GFP. Now I've got my 3 optical configurations that are presets for, I'm actually going to change this to the optical configuration we used, GFP FW. So this is the filter wheel GFP, not the filter cube one. And now that we have everything ready to go, we can just hit run now, and it'll take images at each one of those presets, which is exactly what it did. We've got our DAPI, GFP, and DS Red. So this is how you take an image with the wide field system. At this point, you've got an ND2 file, which is your project file in Elements. You can save, again, as a TIFF file if you'd like. You can save it as a JPEG and so on. But I think for this video, I'm going to leave it here. If you have any questions, please leave a comment below. Otherwise, I'll see you next time. Thanks for watching.